Good evening, everyone. Apologies for the delay. I had some issues connecting my laptop for the projector. Hi, my name is Anindita. I work as a data scientist at Red Hat. And prior to that, I was working with Tata Research on some research problems around NLP. I have more than a decade of experience in applying NLP solutions to real-world problems. So today my talk is around, something very interesting, which is around, I'll be sharing the design blueprint of how to design explainable AI solutions. I've kept the flow of my talk really simple so that, people who even don't have an AI/ML background can relate to the talk. So let's start. So I'll just set the agenda for the day. So why do we need explainable AI in the first place? So, I mean, it's not unknown to anyone, right? We have very powerful models today. We have state-of-the-art LLMs, SLMs. They are very good, but we still don't understand what is happening under the hood, right? So, and explainability can never be, equated with accuracy in that way. So like when we get a prediction from a model, we just don't know why it made that prediction. And in real world use cases, like for example, in manufacturing or healthcare, these questions really matter. Otherwise, it is hard to incorporate trust in these systems, and the user will always be in a doubt that if I cannot explain the prediction of my model, how do I really deploy it really? And we'll be also looking at two very popular explainable AI frameworks, Lime and Sharp. And then we'll understand the limitations of those frameworks, and we'll look at something more advanced called as the knowledge graph approach that will bring in to the domain expertise in place. And then I'll walk you through a very simple Python demo to compare all these three approaches. And finally, the key takeaways from the talk. Okay, so I think there were many talks around, trustworthy AI systems, black box problem, and all. So most of you must be familiar with this term, black box. So most of these models, like coming to the history of AI/ML, we didn't have deep learning earlier. We used to have, traditional AI/ML models. It started with linear regression, logistic regression. In those models, we could at least trace what is happening. We had some level of control. But then came the era of deep learning, and today we have very sophisticated LLMs. But we just import those libraries. They are completely black box to us. We don't know what is happening. And even if they are making certain predictions, we cannot rely on those, or we cannot justify. So that becomes, a compliance problem in most of the domains, and deploying AI in real world becomes a challenge at the enterprise level. So basically, if you look at deep learning, it's basically how the brain functions. So explainability, what it tries to do is it tries to mimic the human reasoning process so that certain ontologies can be created, and we can actually trace the behavior of how a certain prediction was made. So in risk-critical domains especially, like healthcare or manufacturing, this becomes a very important question at the stakeholder level. So today, in today's ecosystem, the way AI is being deployed at the enterprise level, this is not an option. Explainability needs to be there. Otherwise, if we don't have that kind of transparency, we lack the adoption of the AI in the first place. Okay, so I'll start by two very simple techniques which started this explainable AI revolution in the past. So the first is Lime. So Lime is nothing but local interpretable model agnostic explanations. So by model agnostic, it means that Lime fundamentally treats any model as just as a black box. It can work on any model, and it applies some very simple mathematical assumptions to develop its own explainable AI reasoning behind it. So as you can see in this simple graph, so very simplistically, if you want to mathematically, understand AI, what we are trying to do is y is equal to mx plus c, starting with, very simple representation of a model. So we are predicting y against our input features x. So what Lime does is it considers a single instance of the model, and it tries to, build a simple local explanation model around it. So basically what the maths behind Lime is that a complex model is very non-deterministic. It is not really linear in nature. But Lime says that in a small part of a data point, that entire local hood becomes a linear model. So what it does is, suppose, consider that I am the owner of a factory and I want to understand that suppose my machine is dependent on a lot of IoT sensor data. So we have, say, vibration sensors, we have temperature sensors, and I want to understand that why my machine failed at a particular point. So suppose the temperature reading of a temperature sensor once, say it led to a particular prediction. So what Lime will do is, it will just tweak the input data a little. It will create multiple local points around it and then observe that for a particular value of a sensor, what was the output. It'll tweak it a little more and then understand what was the output. So around a simple local point, it will develop its own linear explainability model. So mathematically, that is what Lime means. So that is what is explained in this slide as well. So what it'll do is that simple linear model, it will just try to understand the weights of the sample which are close to the actual instance, and it will try to generate a local explanation at an instance level. It will not try to average out all the results, but Lime is just a local prediction model in that way. So I was talking about this machine failure problem. So intuitively, this is how it will look. So it will look at sensor data here for sensor 1, 2, and 3. So it will try to understand that due to which sensor the model had a particular prediction. So from this simple example, you can see that sensors 1 and 3 had a more positive effect on the model. But this still looks incomplete to us. We need something more. This is just the what of the problem. We still don't know why it led to that particular prediction. So like I said, so Lime is, the limitations are there for Lime. So the first limitation is that we don't have a average idea, or we don't know at the global level what is happening. And the next thing is that we have to generate explanations across all predictions. So the explanations are locally generated. So with every input data sample, the explanation varies. So that is not something very consistent, and we cannot really use it that much in the real-time enterprise applications. So due to its simplistic nature, scientists develop something more after Lime. So we'll talk about the next technique, that is SHAP. SHAP means Shapley additive explanations. So basically, the intuition comes from the game theory problem, or you can imagine a very simple example, like for example, you're going to a party and then the total bill is divided fairly amongst people, right? So that is the most layman explanation of what SHAP does. So it understands that which features contributed to the total prediction, and which features were a positive contribution, which were a negative contribution. So this weighted feature model generates the prediction for the model. So basically, it is assigning each input feature a contribution score, just like we do in cooperative game theory. Yeah, so that is about the mathematical intuition for SHAP. So now all of us understood so far that Lime and SHAP, they are just related to the data. They are just telling us that, okay, due to some mathematical features, certain scores, the output generated a certain prediction. But we still don't understand that what led to this thing. So we still don't understand the semantic reasoning behind what led to that prediction, or there are no logical chains involved in that process. In fact, recently there was a research paper also that all of us use prompt engineering. So we generally use chain of thought prompting. So even that is not explanation generation in the real sense. So we need something deeper. And with every use case, we need some kind of domain expertise involved in our use case. And based on domain knowledge plus data science knowledge, we can combine these approaches and then only design something scalable. So that is where knowledge graphs come into picture. So if you must have heard, there are certain knowledge graph tools for constructing knowledge graphs or ontologies out of your domain data. So basically, what knowledge graph does is that your entities that you want to predict, they are represented as nodes in the diagram, and why a particular entity is related to another entity, it generates in form of a causal or a correlation relationship, which are the edges of that diagram. So generally, Neo4j or Network X are the open source tools which are used to design these knowledge graphs. So it closely mimics how a human would approach a problem, and try to develop a certain network or ontology around the problem. So in a nutshell, this is what we have. Like, for example, if I want to again understand, take my factory use case again. So for example, if I want to understand finally why a machine failed, and I have input data of several sensors. So for, temperature sensor, it will create a small submodel. For the, vibration sensor, it will create another model. For, say, wear and tear sensor, it will create another model. It will combine all these things in the form of a complex knowledge graph and, generate some kind of a structured or, step-by-step multi-hop explanation around the problem, so that if I say to my maintenance staff that a particular machine of mine has failed in the factory, naturally I'll get a question that why it failed, right? So then I can generate some justified reasoning around that. So that is the intuition of knowledge graph. So without much delay, I'll run into a small demo that I've prepared so that I can explain you these things in a little more detail. Yeah, so basically I have created a synthetic sensor data set for predicting why my machines failed. I have trained a very simple, random forest classifier around that. And I've tried to compare these three techniques that I told you, LIME, SHAP, and the knowledge graph-based approach. So basically, I'm just creating a synthetic data, and I'm assuming that I have 8 sensors. And I'm assuming that, if the output of the first 3 sensors is above 1.5, then that is an anomaly and my machine fails. And that is how I'm trying to create this data set and predict my target variable called fail. And I've used, for normalization, I've just used the simple Z score to detect anomaly in my sensors. So, and I've, just for people who are not much aware of Python, there is a scikit-learn library already in Python, which, already has the code for most of the models. I'm using random forest here, which is like an ensemble technique of multiple decision trees. So I've just, imported that library, and I'm just trying to create my feature set. So I'm just dropping my, y prediction variable called fail, and I'm just, trying to define my feature set for this problem. So model.fit, what it does is, it will just create a model based on that particular input data set. And using joblib, we can just dump that model file into a pickled file. And then understand the output. So first, I'll try to generate the SHAP output for this. Yeah, so you can see the SHAP output looks something like this. So SHAP, like I told you, if I have to give you another simple example of, LIME versus SHAP. So for example, a doctor, tells a particular patient that, heart attack happens due to stress. So, stress becomes, average or a very global level reason. So that is what SHAP does. So it says that on an average, across all predictions, sensors 2 and 1 are responsible for most of the failures in my machine. So understand SHAP in that way. And what LIME will do is that for every prediction, it will try to generate a reason. So again, if I take the doctor example, suppose I have to say that my particular patient 1 has a heart attack, say due to high BP. The next has due to high cholesterol. So that is a local level explanation. So that is the primary difference between LIME and SHAP. So, and these are, very well encoded into very good Python libraries for use. Then I'm generating, LIME local level explanations for the same thing. So in LIME, yeah. And then what I'm doing is using Network X, I'm trying to build a knowledge graph around the same problem. So you can compare here SHAP versus LIME. So in LIME, you can see that it worked at a local level, that due to sensor 1, there was a positive class, and due to sensor 3, there was a negative class. So we understand exactly what are the weights contributing to those explanations. But these still work at the data level. There is no reasoning, there is no domain level knowledge involved in these things. So the user does not get the complete idea that why exactly a particular prediction was made, why exactly my machine failed or did not fail. So there is this network X library, and we can add certain nodes to that, like I explained you, and generate certain explanations around that, like how they connect for the reasoning. And then we can create some kind of a this is a very simple knowledge graph, for example. So till now, SHAP and Lime could only tell me that sensor 1 and 2 could generated the machine failure, but it did not generate, this kind of a reasoning path that what led to that failure of machine. So for example, for sensor 2 and 3, they were basically correlated to overheat that caused the machine failure. So this is the kind of, multi-step correlation-based reasoning, or sometimes, a causation-based reasoning. So causation is all about cause-effect reasoning. So something led to some another problem, and correlation is about how just the two variables vary with each other. So for example, if I have to understand in more detail, so sensor 1 correlated with vibration that caused a machine failure. So this is a very simplistic example. In real life, more complex knowledge graphs can be generated using better tools like Neo4j. So they can, create more multi-dimensional knowledge graphs, and the user can also using, something called as cipher queries, query on that knowledge graph directly to understand what is happening internally in the application. Yeah, so So this is again, a very quick comparison of what is the difference between SHAP versus Lime versus KG. So as we can understand that both SHAP and Lime are very, data dependent techniques, and it's just very statistical. We don't understand what is happening at the semantic or the conceptual level. So if we want to understand, the root cause of why our predictions in the model of the AI model were not up to the mark, we need to create ontologies internally in our data. Of course, it's not that easy in real life. Data is messy, and we have to identify what are the points of interest which we mark as entities in the nodes. We have to identify what caused those problems. So we saw a very simple example in the manufacturing domain. It could be extended to other domains as well. For example, if I take the example of a support business, customer support business, so multiple tickets can be related to each other. They can be nodes in the system. And why those tickets were related to each other, that can be modeled as a cause-effect edge relationship. So such kind of multiple complicated ontologies can be created, and the data itself can be represented in the form of a graph. And so that better, root cause analysis can be done, and we can, get help of the domain expert to understand what is happening in our end-to-end use case. So yeah, so that's all about it. So if this was just a design blueprint to how to develop knowledge graph based applications and make your AI more scalable, maintainable, do better root cause analysis out of it. I'm also working on a project using Node.js, and I'm using some ontology based things in that using Neo4j. So I'll share my project with you, and if anybody is interested, I'm open for collaboration. Because in real life, in demo it looks easy, but in real life the data is very messy, and creating the right ontology out of it is still an open problem, and there is still a lot of research going on in that area. So these are some very good research papers which I'll recommend you to read, and always open to collaborations. So yeah, thank you so much for your time. My demo code is shared on my GitHub, and I can be reached out on my LinkedIn as well as mail. So I'm open to Q&A if there's any. Yeah. Yes, yes. Yes, yes. So this, yes. So I'll share my project also with you. So I am basically using Neo4j. That's an open source, graph database tool. So we can represent our data in the form of these nodes and edges. Right now, what I showed was a very simplistic case for a demo. But like I told you, in real life, defining those nodes and edges becomes a challenge. And that comes not only by knowing data science, or you can not just put it into chat GPT and create the ontology. That is actually coming by understanding what is your use case, understanding what is your data, and not from my experience on all data, such good ontologies can't be created also. It's still an open-ended research problem. So, and if the ontology is created, like we know, all of us know about RAG. So many people are still working on this graph RAG. So if they can, instead of vector DB, if they can put it in the form of a graph database, they get better responses from their chatbot. So I think the bottleneck is, creating a good ontology, which for which I don't know if there is any, automated AI tool. It requires some domain expertise. Yeah, so we'll connect offline if you want. Thank you. No, no, no. I meant to say that I cannot explain the internal parameters of the model, but I can explain that why, it led to that output. I can reason the behavior, like the human things, with the knowledge graph. I can understand my data better. So for example, like in my sensors example, right? So if you have this IoT domain use case, so if you just run any model, you will just know that why your, say, sensor failed or machine failed at a particular point. You don't know what were the features which were the top contributors. So Lime and SHAP solved that problem. At data level, it told that what were the features which were most important, leading to a certain particular prediction. But it didn't tell you why. Training data. Training or your entire data as a whole, so you can explain the reasoning behind why model made a particular prediction. It is still not explaining that what are the parameters used in training the model. That is a different problem. No, no, no. LLMs don't do it directly. There are some open source tools. So one very good tool is Neo4j. So, and there you have to, manually design your graph. And then using Cypher, you can query on that data and you can get quick responses to some of your questions. Like why your model is behaving in a certain fashion, or why your data is leading to a particular output. Why changing in your input data is leading to some output. Why X1 is leading to particular Y1, why X2 is leading to particular Y2, that way. It is. But it is worth, because in real life, if you see, today we have RAG. And the problem that we face is that the token limit problem of the models, right? So it chunks the data. So when you chunk a very huge data set, you lose the semantic level information, you lose the continuity of that data. And in real life, if you see, in domains like, this manufacturing, healthcare, this data is very interconnected to each other. So if you understand the correlation and causation between that data, and if you can at least represent some part of data as an ontology, then it will help you design better chatbots. It will help you design better RAG. Because graph RAG is used in the industry today. So that way. Okay, thank you. Okay, so if there are no more questions, thanks a lot for your time. And I'm available offline for any collaborations or further questions. Thank you.